Okay, I hope you can see this PowerPoint. Okay, so diffraction. Okay, this is Fresnel and Fraunhofer diffraction. We'll come to this later. Okay, so this is the thing which we have been talking about. Okay, so so let me read the figure caption: diffraction of light through wide and narrow openings. Okay, you see, so this opening, it is quite large. Okay, quite large means very large. Okay, and if light is traveling from, suppose, left to right, what will happen? So light is of course passing through this opening, this quite wide opening, but this, you see, the deviation of light is not very much pronounced. So light is moving in a straight line. This is the very straight path of motion of light, but once it is encountering this wide opening, so it shows some little bit of deviation. Okay, it is not a huge deviation, little bit of deviation. Okay, but this scenario is completely changed when the opening is much narrow. This opening you can see here, this opening is much narrow. Narrow means okay, sorry, narrow means this opening is of the order of wavelength of light. Okay, so now what happens? These light waves which are traveling in a straight line from the left, and this opening is very narrow. What happens in that case? The light waves, they deviate widely. You see the difference of deviation between this figure and this particular figure. So here they are deviating much more from their straight line, from the straight line path, because we know light travels in straight line, or that is also called the rectilinear propagation of light. So here light waves are traveling much wider than in this case. Okay, so that means this deviation or this diversion of light from its original path is much more pronounced than this particular case. Why? Because in this particular case the opening is quite wide, but in this case the opening is very narrow, and because of this narrow opening, this diversion is very pronounced. Okay, so I hope this is clear to you. These are the same things which we have already read from the note which was given to you. And then we also learned about the definition of diffraction of light. So you can see you have an edge here, okay, straight edge, and on the from the left side, the light is traveling from the left side, the light wave. What is going on now? Now it encounters this particular obstacle or edge. Obstacle means it stands in the path of light. And as we have already learned, that this obstacle should be opaque in nature. Opaque means light does not pass through it. Okay, this is opaque, it blocks light. Okay, so anyway, so at the edge of this obstacle, at the edges, what happens? Light begins to bend. They begin to bend in this way. Earlier light was traveling in a straight line. Earlier light was traveling in a straight line like this, but now light begins to bend along this. Okay, and this type of bending phenomenon of light is known as diffraction of light. Okay, so the bending of light about an edge to geometrical shadow is the definition of diffraction of light. Okay. So I hope the definition of diffraction of light is clear to you now. So this figure. So here the deviation is not very much pronounced because this is a wide opening. Here it is pronounced because this is a narrow opening, which generally should be of the order of light wavelength. And therefore, in this case, light shows quite pronounced deviation. And in this case, this is the bending of light. Okay. In this case, you have put an obstacle in the path of light, and the light bends around this edge, and that is the definition of diffraction of light. Okay. I hope this is clear. Then after this, okay, I will come back to this PowerPoint soon. But now I'm going to present you the same document which I was presenting earlier. Now, differences between interference and diffraction. Okay. So you have any questions so far from here? If not, then we can move to the differences between diffraction and interference. Okay, so interference we have learned earlier, and but more or there are some similarities, but there are also some differences between them. Okay, so let us read. So difference number one is interference is the result of interaction of light coming from two different wavefronts originating from same source. Okay. Diffraction pattern is the result of interaction of light coming from different parts of the same wavefront. Okay. So interference, we know that we have two wavefronts, and when they superimpose with each other, they form interference patterns. So interference patterns are nothing but increase or decrease in distribution of light energy, which we discussed in the last class as well. But what is the main difference? So you see different wavefronts. So interference happens between light waves from two different wavefronts. But diffraction pattern is the result of interference of light coming from different parts, but of the same wavefront. Okay. Different parts, light is coming from different parts from the same wavefront. Okay. So in interference, two different wavefronts are involved, but in diffraction, only one wavefront is involved, and light comes from different parts of the same wavefront. Okay. So regarding this, there is one principle called Huygens Principle, Huygens, Huygens Principle. So I think you should refer to that Huygens Principle, which is the definition is like this, that different parts. So remember the Huygens Principle, and then from there actually the concept of diffraction of light comes. So it was something like this, if I remember well. So it was like different parts of the same wavefront can act as sources of wavelets. Okay, so different parts of the same wavefront can act as sources of wavelets. Wavelets means waves, light waves, nothing but light waves. So in diffraction, what has happened? So these wavelets, they are originated from different parts of the same wavefront, and they form some pattern. Okay. And how is it different from interference of light? Because in interference of light, two different wavefronts are involved. Okay. So is it clear? So this is the very basic difference between interference and diffraction. Okay. But there are more differences. So let me read them out. So difference number 2 is interference fringes may or may not be of same width. Okay, so they are of different, they may be of same width but may not be of same width. But what happens in diffraction? So these writings are not so good, but still I hope you'll be able to understand. So diffraction fringes are not of same width. Okay, so in interference, the interference fringes like bright or dark fringes, whatever, so they may be or may not be of same width, but diffraction fringes are not of same width. Okay. So the third difference between interference and diffraction is in interference, points of minimum intensity are perfectly dark. Points of minimum intensity are perfectly dark. Okay. But in diffraction, points of minimum intensity may not be perfectly dark. Okay. So this is the third difference, and the fourth difference is there is another difference. In interference, all bright bands are of same intensity. Okay. In diffraction, all bright bands are not of same intensity. So these are the four major differences between interference and diffraction. Okay, so I'm revising interference and diffraction. First is the definition. What is definition of interference? Interaction of light coming from two different wavefronts, okay, of the same source. Diffraction, interaction of light coming from different parts of the same wavefront. Okay, and for this, please refer to Huygens Principle, Huygens. You can note it down. Maybe I have also given you in some note what is Huygens Principle. I forgot, but I have to check. Okay, but anyway, you yourself can also check. Okay. So second one is interference fringes may or may not be of same width. The may be or may not be of same width, but diffraction fringes are always of different width. Okay. So in interference, points of minimum intensity are perfectly dark, but in diffraction, points of minimum intensity are not perfectly dark. So in interference, all bright bands are of same intensity, but in diffraction, all bright bands are not of same intensity. They may be of different intensities. Okay. So you should remember all these 4 points. So very important. Because if you are you have earlier learned interference, now we are learning diffraction, then of course there a question may arise. So what's the difference between these two? So you have to mention these points. Okay. Okay, I will in the meantime I will take some screenshots here, and then screenshots just for my record, and then I'll return back. So just give 2 minutes. Okay, so I have taken some screenshots. Then maybe we can move back to the same notes. So there are broadly diffraction types. So let us learn about diffraction types. So broadly there are two types of diffraction. So which are known as Fresnel, Fresnel. So it's a French word. So it's pronounced as Fresnel. Okay, and Fraunhofer type. Okay. So Fresnel and Fraunhofer type. So let's learn about these two different types of diffraction pattern. So now Fresnel diffraction, in this type of diffraction, so what is Fresnel type of diffraction? Let me read out, and I will show you a figure from PowerPoint separately. In this type of diffraction, the source of light or screen or both are at finite distances from the obstacle or aperture. So for diffraction, we always need an obstacle or aperture, right? That is what we have just learned. So in the Fresnel type of diffraction, the source of light, there must be a source of light, and the aperture, or okay, the source of light separately and the obstacle or the aperture. So at least one of them should be at a finite distance. Okay, either the source of light should be at a finite distance, or the obstacle slash aperture, whatever we are using to get our diffraction pattern, that should be at a finite distance. Okay, so no lenses are used to make the rays parallel or convergent. Okay, so this is an important point to remember. No lenses are used to make the rays parallel or convergent in Fresnel type of diffraction. Why? Because either the source of light is nearer or the screen is nearer. Okay, screen is nearer or at finite distances from obstacle or aperture. Okay, and therefore there no lens is required. So why the lens thing is coming into picture, I will show you in the figure. Okay, so no lenses are required to make the rays of light convergent or parallel. Okay, the incident wavefront is not plane, but it is either spherical or cylindrical. Okay, this is something you should remember also. The incident wavefront, the wavefront means the wavefront from which the wavelets are generated, the wavelets which generally take part in diffraction. So incident wavefront has a size which is either cylindrical or spherical. Okay, as a result, the phase of secondary wavelength is not same at all points in the plane of aperture or obstacle, causing the diffraction. Okay, so the phase of all the wavelets, secondary wavelet means these are the wavelets which are generated from the same wavefront, and that is not same in the plane of aperture, because they are either spherical or cylindrical in shape. They had been similar if they had been plane wavefronts, but they are not plane wavefronts. They are either spherical or cylindrical. So they have different phases at the plane of the obstacle or aperture from which diffraction is caused. Okay. The resultant amplitude at any point of the skin is obtained by what did I write this? Mutual. I think this is mutual. Yeah, mutual interference of secondary wavelets from difference elements of the unblocked wavefront. So this is nothing but more or less the definition. This last line is more or less the definition of diffraction. The resultant amplitude at any point on the screen. The screen is always there. I will show you what is a screen. Is obtained by mutual interference of secondary wavelets from different elements of unblocked portions of wavefront. Okay. There is some description of this phenomenon, and the description is also will also be understood more from the figure which I will show you next. To explain this, Fresnel made following assumptions. Okay, what are the assumptions? There are several assumptions. A wavefront would be divided into a large number of small elements or zones called Fresnel zones, each of a small area. Okay, so a wavefront is divided into a large number of small areas which are also known as Fresnel zones. Okay, the resultant effect at any point P on the screen will depend on the combined effect of all secondary waves originating from the various zones. Okay, so the resultant effect at any point P on the screen will depend on the combined effect of all secondary waves. Okay, so what will be the intensity of light or resultant effect at the point P on the screen? P on the screen, you will see in the figure. It will depend on the secondary waves. Okay, secondary waves which will be generated from different parts of the wavefront. Okay, wavefronts means various zones. Okay, from the various zones means the Fresnel zones. Okay, so the second point is the effect at any point due to a particular zone will depend on the distance of the point from the zone. So at a point on the screen, what will be the effect due to a particular Fresnel zone? That will depend on how far is the point on the screen is from the Fresnel zone. Okay. And there are some more descriptions from the figure given here. So the effect at P will also depend on the obliquity of the point with respect to the zone. Okay. So the obliquity factor is proportional to 1 plus cos theta. So obliquity means how much angle it makes. Okay, so because you know oblique is not a straight line, but it is kind of some angular deviation from a straight path. Okay, so the obliquity factor is proportional to 1 plus cos theta, where theta is the angle which PE makes with EO. So what are PE and EO? So I think those figures have been given to you already, and I also will show you. Considering an elementary wavefront at E, the effect is maximum at theta equal to 0, or theta equal to 0 means cos theta is equal to 1. As we move from O towards P, the value of theta increases and hence resultant effect decreases. Okay, so that means theta increases means move from O towards P, theta increases and resultant effect decreases. So what is this? I'm going to show you actually, because without okay, let me find the figure first. Yeah, I have the figure. Okay, so let me read the last paragraph, then I'll go to the figure. Okay. Fresnel type of diffraction is produced when light suffers diffraction at a straight edge or a narrow slit or a thin wire or a circular hole or obstacle. An application of this type diffraction is made with construction of zone plates. So zone plates are themselves different concepts. Okay, so I'm going back to the figure. Just give me a moment. So can you see this figure? I hope you can see this figure. Okay, so this one I have taken directly from your Google Classroom note. So okay, so S is the source of light here. Okay, and this CEF, this straight line you see, that is the obstacle or aperture in the place of light which is originating from the point S. Okay, and RT, this you see TPOR, this is nothing but the screen on which we will obtain diffraction pattern. Okay. AB, AB is a, you see, it's a spherical or a spherical surface. Let us assume that this is a spherical surface. So that is the wavefront. So because we have just learned that in case of Fresnel diffraction, the wavefront which is incident on the aperture or the obstacle is generally of which shape? Spherical or cylindrical. Okay, so let us assume that this is a spherical shape. It's the part of a sphere. Okay, AB, and this is the obstacle, the CEF. Now this is the angle theta, the obliquity angle. Obliquity means how much. If a ray of light S travels from left to right like this, as you can follow my cursor, the ray of light moves in a straight path of O, okay, EO, like S to E, E to O. This is otherwise the straight path of light, the original rectilinear propagation of light, because we know that a light wave always travels in a straight line. Okay, but now when we are talking of diffraction, there is an obstacle or there is an aperture. The aperture should be of the dimension of wavelength of light. So what happens? The ray of light suffers diffraction. It suffers some deviation along the path EP. EO is the original path of a ray of light in a straight path, but in this case, the light will also undergo deviation or diffraction and it moves along EP. And suppose this EP ray of light makes an angle of theta, as you can see here, theta, with the original direction of light. Okay. Now, I am reading out the line. The obliquity factor is proportional to a quantity 1 plus cos theta. If theta is 0, that means the obliquity factor will be how much? Proportional to 1. If theta is the angle which PE makes with EO. Okay, let me check. PE max with EO, yes. So then theta is the angle which, okay, the considering an elementary wavefront at E, the effect is maximum at O as theta is equal to 0. Okay. Okay, now you see PE makes an angle of theta with EO. Okay. Now when theta is 0, what is the this thing, obliquity factor in that case, or what is the influence on the effect? It will be 1 plus cos theta. 1 plus cos theta is the factor on which the effect depends, the effect of diffraction. Okay, so it will be 1 plus cos theta, and if theta is 0, when is theta equal to 0? When the light travels along a straight path. That means the angle between PE and EO is 0. In that case, the obliquity factor will have a value of 1 plus cos theta. Cos theta is equal to 0. That means cos 0 means 1. That means 1 plus 1, it will be equal to 2. Okay, that is the maximum value of the obliquity factor. That means at O, the effect of diffraction will be maximum, okay, or the more or less the intensity. Okay, but as you keep on increasing from O to P, keep on moving from O to P, what will happen? Theta value increases. Okay, if theta increases, what will happen? Cos theta will become smaller than 1. Okay, because you know that the value of cos theta can be between plus 1 and minus 1. So cos 0 is plus 1, and if you go to higher values like cos 30, cos 45, cos 60, cosine 60, like that, in that case, the value of cos theta will be lower than 1. And if it is lower than 1, the obliquity factor will also get on becoming smaller. Okay, in that case, what will happen? If you move from O towards P, in that case, the resultant effect of diffraction or the effect of this interaction of light waves from the same wavefront will become smaller, or the effect will be decreased. So now you tell me, you have understood this figure or not? Not from the note which is given. So the resultant effect of interaction is maximum at the point O, because in this case the light is traveling in a straight line, okay, without suffering any deviation or diffraction. The light source is S. But since the aperture is very narrow, what happens? Light also undergoes some deviation. Then there is an obliquity factor, or there is an oblique angle of theta. Oblique angle theta means the angle which the deviated ray of light PE makes with the straight path of light. Okay, so at O, the factor is the cos theta is 0 at O, because if you just move the straight line PE back to O, theta becomes 0. If theta is 0, cos theta is 1. That means the resultant effect is dependent on 1 plus cos theta. That means 1 plus cos 0. Cos 0 is 1 again, so 1 plus 1 is equal to 2. But as you move outward from the point O towards P, what will happen? Theta will get on increasing. Theta will increase, but cos theta will decrease. If cos theta decreases, it will be the final value will be less than 1 plus cos theta will be less than 2 now. In the maximum case, it is equal to 2, 1 plus cos theta, but later it will get smaller than 2. And in that case, the resultant effect decreases at the point P. Okay. And it will keep on decreasing if you go on moving upward like this. Okay. So at the straight line, at the straight path O, it is maximum. Then if you go on, even if you keep on moving downward to OR, or if you keep on moving upward or away from O along OP, OT, so the resultant effect due to diffraction goes on decreasing. Okay, I hope this is clear to you. Just refer to this figure. Okay, first you read the note, and simultaneously you also refer to this figure. Okay, so I am stopping this one. Now the next type of diffraction is Fraunhofer type of diffraction. Okay, so there are two types of diffraction. Fresnel type, we have learned about the Fresnel type. So now what is the Fraunhofer type? So let me read out. In this type of diffraction, so you note down the difference. Okay, what was the definition of Fresnel type diffraction, and what definition of Fraunhofer type diffraction we are going to learn now. In this type of diffraction, the source of light and screen are effectively at infinite. Okay, so this is infinite. Maybe my writing is not so good here. I have to cut something. The source of light and screen are at infinite distances from the aperture or the obstacle. In the Fresnel type, in the earlier type, what was that? The source of light or the screen was at finite distance from the obstacle or aperture. But in this case, they have to be at infinite distances, okay, which causes diffraction, or from the obstacle or aperture, which causes diffraction. So this may be achieved by using two convex lenses. So we have to use convex lenses because why? Because the source of light is at infinite distance, the screen is at infinite distance. Therefore, we have to make the first convex lens. What it does, it makes the rays of light parallel or convergent. The rays of light which are coming from the very far away places, very far away source. Okay, and at the same time, what is this? The screen. The screen is also at a very far away place, and therefore we need another lens to converge the rays of light to the screen. Okay, so I will show you in the figure, it will be clear to you, but for now you just remember what is the definition. So apart from the definition, we need two convex lenses. Okay, so the reasons are given. One, to make the light from the source parallel before it falls on the aperture, and the other to focus the light after diffraction on the screen. Okay, so after getting diffracted, the light has to be made incident on the screen. Therefore, we need the second lens. Okay. This incident wavefront is plane. Now, this is a difference. The incident wavefront is plane in this case, because in the earlier case of Fresnel type diffraction, the incident wavefront was either spherical or cylindrical. But in this case, the incident wavefront is plane. Okay. And secondary wavelets, which originate from the unblocked portions of the wavefront, are in the same phase at every point in the plane of aperture. Okay, this is another difference. So in the earlier case, the wavefront was, earlier case means in case of Fresnel type diffraction, the wavefront was spherical or cylindrical, and therefore the phase of different portions of the wavefront were different in the earlier case. But in this case, the incident wavefront is plane, and therefore the phases of different portions of the wavefront are same. So they are in the same phase at every point in the plane of aperture. Okay, so this is a difference between. So if I ask you in the question, so mention two differences between Fresnel type diffraction and Fraunhofer type diffraction, that you should be able to answer, I hope, by now. Okay. The diffraction is produced by interference between parallel rays, which are brought into focus with the help of convex lens. Okay, I will show you in the figure. The most important example of Fraunhofer type diffraction is made in the case of plane transmission grating or concave reflection grating. Okay, so one of the examples of Fraunhofer type of diffraction is plane transmission grating, and in your next class, next video class, most probably it will be on Friday. Friday, let me see, Friday afternoon maybe, because Friday morning I have to attend one seminar. Okay, so in morning I will not be able to take your class, but I will try my best to take a class in on Friday afternoon. Okay, so in that case we will discuss about plane diffraction grating, okay, or transmission grating. So that is also going to be a very important concept. Okay. Okay, so have you understood? Okay, now I am stopping this, and I am going to the PowerPoint, and I will explain the PowerPoint to you. And this particular figure you'll see, okay, Fresnel and Fraunhofer diffractions. So the caption condition for Fresnel diffraction and Fraunhofer diffraction. Okay, so Fresnel diffraction, what is going on? You have a source as here. You have a slit through which light passes, and light gets deviated from the linear path, and they fall on the screen. The screen is this one at the point P. Okay, and both the source and the screen are at least one of them is at finite distance from the opening. Okay, either the source or the screen, and no lenses are used in this case. Okay, I hope this is clear. But now the situation is a bit different if we are talking about Fraunhofer type of diffraction. Okay, in Fraunhofer type of diffraction, although you can see that the source and screen are at not very far away distances, because on a plane like this we cannot draw, we cannot show that source and the screen are at very far away distances from the obstacle. Therefore, just for your understanding, consider that the source and the screen are at very far away distance from the slit or the aperture. Slit means there is an opening here through which light suffers diffraction. Okay, and there are two lenses we have already learned. This is the lens 1 and this is the lens 2. So what is the function of this lens? So the function of this lens is that it converges the rays of light which are coming from infinity. Infinity means the source. The source is at infinity and the rays of light is coming from infinity and getting incident on this lens, and they are then incident on the aperture, and on the aperture they are getting diffracted. Okay, and the rays of light are getting diffracted, but at the same time there is another condition, which is the screen itself is placed at an infinite distance. And in that case, how should we get all the rays of light at the same point P? In order to do that, what we should do, we should place another lens in the path of this diffracted rays of light. In that case, the rays will get what to say, that what is that word? Converge. Sorry, I forgot the word. In that case, the rays will be converged by this second lens, and they can be collected at a given point on the screen. Suppose that this given point is P. Okay. And why are we using two lenses? Because the source and the screen are at infinite distances from this aperture. Okay. The first one is the lens 1, lens 2. Lens 1 collects the rays coming from the source and converges them, or gives them a direction towards the aperture, and from the aperture they get diffracted, and then these diffracted rays of light are sent to this lens, and from this lens converges the diffracted light, and they are incident on the screen at P, and we can see the diffraction pattern on the screen. And one more difference was that here the incident wavefront is generally spherical shape, but here the incident wavefront is plane shape, and therefore the phase of different portions of the wavefront are same, but here the phases of different portions of the wavefront are different. Why different? Because the incident wavefront is spherical, and in this case the incident wavefront is plane wavefront. Okay, so these are the two major differences between Fresnel and Fraunhofer type of diffractions. So in the next class, I am planning to discuss about this plane diffraction grating, which is an important concept. Okay.